As a second talk, we have Ricardo Rodríguez. Are you here, Ricardo? Awesome.
Yes, I am. Yes.
And it's on the evaluation of the executional power in Windows using return-oriented programming or ROP programming. We can see your slides. They are not full screen yet.
Okay, now I'm putting in full screen. Now it's in full screen.
Well, I still see the bars.
Okay, just a second. I think then I have to share the full screen, right?
I don't know. I'm not a Mac user. But that may be the case.
Yeah, let me try.
On Firefox, it actually stuck to the window. Now I see your full screen. Cool. Yeah, they are full screen now. So please, Ricardo, take it away.
Okay, so thank you for the introduction. I'm going to present this paper, Evaluation of the Executional Power in Windows using return-oriented programming. So I'm going to follow this outline for the talk. Okay. So moving to the introduction, we are talking about the return-oriented programming attacks, which are a type of counter-reuse techniques introduced in 2007 by Sachan. These kind of attacks allow us to allow an adversary to hijack the control flow of a victim program without injecting the code. These attacks are known to be incomplete. This means that we are able to perform any kind of arbitrary computation with them. So first, some terminology that we need to understand. We have ROP gadgets, which are relatively short code snippets, which are already present in the victim's memory space, and end in an assembly instruction that changes the control flow of the program. For instance, a read instruction in Intel assembly, or a jump instruction. And then we have also a ROP chain, which is just a chain of ROP gadgets. So the idea of ROP is that if we have this kind of code in the memory, that can be a legitimate instruction. If we start to read this instruction in the second byte instead of the first byte, then we have changed totally the meaning of the instruction. Okay. If you see now, we have here a movement to an address of the value of a register, and then we have a return instruction. So if the adversary is able to write the values into the stack, then the adversary can, for instance, insert these values, which are just instructions, memory addresses, and some arbitrary values. If you see the memory addresses, then I have put here some examples of possible ROP gadgets. Okay, at the end of this of the execution of this ROP chain, then the attacker will obtain this as a result of the execution. So he's able to obtain the values that he wants on the registers. Well, one question that still remains open is how much is the executional power of an adversary? So to answer this question, we have reframe it into other questions, which are these ones. So how often we can find ROP gadgets in any real-world program? And is it possible to chain gadgets for any kind of desired computation? So can we have enough gadgets to emulate any kind of algorithm? As an adversary model, we have thought in a system which has not address space layout randomization of, in case that it is deployed, there is a break for that. The same happens with the control for integrity protection mechanism. So they are disabled, or there is a break for this kind of protection. And of course, the adversary knows the content of the memory address space of the victim program. As contributions of this work, we have defined a Turing-complete virtual language, which we have named ROPLang. And we have used this language to quantify the executional power of an adversary in Windows 7 and Windows 10 in both 32 and 64-bit versions. As a side product of this research, we have developed a software tool which is named ROP3 that takes as input a set of program files set of binary files, and a ROP chain, which is described with the ROP-lang operations. And as a result, as an output, this tool is going to return you the ROP gadgets that make up such a ROP chain that you have defined. So let me introduce you the virtual language that we have defined. This language is composed by a set of virtual operations. These virtual operations at the end are just taking sequence of instructions of the vulnerable program conformed by ROP gadgets and are simulating the operation of interest. These operations are following the Intel assembly notation. So we adhere to the Intel X 32-bit syntax. Okay, so we have first the destiny, and then we have the source registers. Regarding the operations that we have in this language, we have the arithmetic operations. We have the assignment operations to assign values to variables. In this case, variables are logical registers of the CPU, are mainly logical registers. Then we have also the reference operations, which are useful to write or read memory addresses. We have also logical operations, the typical ones that can be simplified to a smaller set, just using the Morgan laws. And we have also branching operations. So we have conditional and unconditional branch operations. Conditional branching operations are a little more tricky that I will explain afterwards. So just for give some examples, these are the kind of arithmetic operations that we have. So we have the addition, subtraction, and the negation, okay? And these are just some ways to simulate this behavior with a ROP gadget, okay? Note that, for instance, here we have the negation of the destiny register, and can be either simulated with the combination of these ROP gadgets plus this other virtual operation, or with directly this operation otherwise. So regarding assignment operations, we have the move and the load constant, so to set values in particular registers or particular memory addresses. And regarding the reference operations, we have the load and the store, typical load and store operations, and logical operations that I have commented before. So regarding the conditional branching, these are very tricky operations. So we need first to get the carry flag in the value of the carry flag in a registry, and then we need to get that registry and add to it, some delta value. Okay, this delta value means the value that we want to jump in case that the carry flag is set to 1, or otherwise it will be the delta value in the assignment will be set to zero, which means that it's not going to make the jump. Okay, and finally we will need also the addition of that value to the stack pointer. So for simulating conditional branching, we will need these three operations followed. Okay. By the way, I forgot to say that for the get carry flag operation, we will need also to add the comparison operations, which means the operation that it wants to perform. As comparison, we have only considered equal comparison or less than comparison, because with this combined, we can do many other comparison operations. And then conditional branching is very straightforward, so we can just load the delta value in the registry, in the destiny registry, and then add this registry to the stack pointer. So just some remarks on this. We have at the moment, this is a non-exhaustive list of ROP gadgets. You can extend this very easily with the tool. As I have commented before, some of these operations are virtual operations, while others are directly ROP gadgets. So we are combining both in order to obtain the behavior. We have assumed that there is no harmful side effects between the sequences of virtual operations. We have also proved that this language is Turing complete. You can find the demonstration in the paper, in which we have simulated a classical Turing machine with the operations. Regarding the tool ROP3, it was developed in Python and relies on Capstone to disassemble the input files. The idea is that this tool already supports the virtual operations that make up the ROP-lang language. The operations, in fact, are defined using the YAML syntax. So you can define your own operations, either as a single or as a multiple YAML files. You can specify also register mask or specific logical CPU registers, and you can also set arbitrary values. For searching for ROP gadgets, the tool uses a similar approach to the Galileo or the algorithm of such. Just to illustrate an example of this file, so here we have the definition of how is the add operation, okay? And here we have the definition of the not operation, and if you see, we can also set particular values to some of the registers. So one of the main contributions of this tool is that allow us to construct a ROP chain being specified by virtual operations. So the search algorithm works in this way. First, it will find all the gadgets that are complying with the operation in the find chain. Then it will build a tree structure considering the order of operations, and then it's going to resolve the data dependencies by traversing the tree recursively in depth first order with backtracking. Okay, at the moment we are working to eliminate the side effects in the chain. So let me illustrate with an example. Imagine that you want to obtain you want to have this chain, this ROP chain. Okay, so you want first to load a constant in a register, then to negate in another register, and then to do an AND operation between both registers. So the tool will look for the ROP gadgets that fulfill each one of these operations. Okay, and then it will start to build the tree. So it will start with the first gadget. I have only shown in the figure. I am only showing the first. Okay. It will assign reg1 to EDX register, and then it will move to the second instruction, to the second operation. Okay. It will start with the first instruction of the one that has been found. In this case, is this nec EBX. So EBX, it will be assigned to reg2. All right. Then it will move to the next one, and then he will start with this and ECX EAX. In this case, it has to fulfill that ECX is the value assigned to reg2, but it's not, because it was EDBX. So it will backtrack, and then it will try with the next one, which again is ECX. So it will not be fulfilled. So it will backtrack and then backtrack again and go to the next. Okay, so in this case, it will get the nec ECX, right? So it will assign the ECX register to reg2. And once it has been done, it will go to the next operation. And in this case, with the first ROP gadget, if you see EAX is not, which is EDX, so it will move to the next one, and then it will finish. Okay, and it will return this ROP chain to the user. So this tool is released under GPL version 3 license. It affects many parameters, such as the maximum byte size that you want for the ROP gadgets, or the final instructions that you want to consider. And it's also a Python 3 library, so you can integrate into your workflow analysis very easily. So you can check on the GitHub of our group to get the tool. Regarding the evaluation, so we have get a subset of the DLLs which are contained in the non-DLL system object. In fact, we have only considered the ones that are common between all the versions of Windows considered for the experimentation, okay? We have taken Windows 10 and Windows 7 in both 52-bit and 64-bit versions. So here you have the specific versions. I'm going to show now you the plots of the experimentation. These are heat maps in which we are showing the percentage of occurrence of each operation within each DLL. These heat maps are annotated, so we are showing the number of results. In case that we have a number of results which is greater than 10,000, we are just showing the most significant digit and the order of it, okay? And the DLLs has been sorted by the byte size. Regarding the configuration of ROPS3, so we have this configuration, a maximum of 10 byte, only read as final instruction, and we have only counted only once the gadgets that are made up of the same sequence of instructions, and we have only considered the definitions that of ROPLAN operations that I have shown you. Furthermore, we have also considered some additional operations, so we have extended the native operations to these ones. If you see, this is just for getting more results on the conditional branching. So it's adding specific values to the stack pointer. So these are the results that I'm going to go fast to the discussion. You can see the graphs on the paper. We have found that branching virtual operations are the least frequent in both architectures. And in fact, there is no results for unconditional branching in 64-bit systems. Regarding the other virtual operations, the results are very diverse. And of course, as other authors claim in the literature, the larger the DLL, the greater the number of results. We have also observed that the number of virtual operations in Windows 10 is always greater than in Windows 7 and in the 64-bit than in 32 bits. This also can be motivated because the difference is in the size of the DLLs. Let me also note here one thing is that regarding the results in 32-bit environments, these kind of instructions can have references to memory addresses that are randomized by ESLR. And we have only considered each DLL with its base address. So these results are highly dependent on the base addresses of the DLLs and that can change when the base addresses are different. This is not happening in 64-bit architecture because of the new address in the form of Intel that was introduced with this architecture, relative RIP addressing. So one question that remains here is to see how ASLR can affect the prevalence of ROP gadgets on the 32-bit Windows systems. So as we have seen, we have very limited results for conditional and conditional operations. And these kind of operations are mandatory to simulate a classic Turing machine. So we have an idea is to relax the data dependency constraints on certain operations just by adding some intermediate assignment operations, for instance, with a move. This will increase our probability of finding some conditional and conditional operations. Of course, this will also add more length to the ROP chain and also can occur more, is more likely to occur more side effects. For instance, consider that we have this as originally defined. So if we add this intermediate register, so we are increasing the probability of having more results. Okay. We have done this with the operations that are involved in the conditional and conditional operations. Doing this, we have found that well, we have some few results on the architecture, okay, for Windows 10, and still we have no results for Windows 7 in 64-bit architectures. In addition, we have also more results on 32-bit systems. This also demonstrates that if the adversary tries to make a sophisticated link of other operations, it will increase the probability of simulating any kind of operation when it's not found directly. Okay, and this kind of extension is very simple using our tool ROP3. So regarding the related work, there are a lot of tools focused on detection and mitigation of ROP attacks. Some other tools focused on offensive technology, and few tools on the generation analysis of ROP chain. Our approach is a simple solution, so it's just make a backtracking algorithm, and it also add this language that allow us to define semantically equivalent operations very easily, and also allow us to automatically generate the ROP chains defined with these operations. So moving to the conclusions. Well, we have defined this virtual language that in which the virtual operations are mapped to ROP gadgets. And we have developed a tool that allows us to find the ROP gadgets and build a ROP chain automatically being specified by the ROP-lang operations. As conclusion, we can say that, well, any virtual operation has been found, and the branching operation is the ones that are being the least frequent in the experiments. In any event, the adversary can make a careful linking of the virtual operations to find any kind of operation that he wants. And as I have commented before, also, and other authors already claimed in the literature, the size of the program file clearly impacts in the prevalence of the ROP attack. So the larger the DLL, the higher number of results. Well, as a future work, we are working now in trying to automatically eliminate the side effects that can occur with some of the ROP gadgets in the ROP chain. And also, we want to extend this work to evaluate the executional power in other operating systems, such as Linux or macOS, among others. And that's all. Thank you for your attention. If you have any questions, I will be glad to answer it.
Awesome. Thank you very much, Ricardo, for your talk. We are a couple of minutes behind schedule. We didn't catch up. So I would suggest we actually take questions over the chat. I do have a couple. And people can actually type them up, and you, Ricardo, can answer them.